limit comparison test. Very similar to direct comparison, but I think a little bit easier. For direct comparison, you're almost guessing, trying to compare the series to another known convergent or divergent series. With the limit comparison test, it relies, I think, a little bit more on the algebra and analysis. So you compare two series, summation of a sub n and summation of b sub n, where the sequences are both positive. If the limit of the ratio of the sequence values is some number, and that number is finite and positive, then whatever happens to one series happens to the other. So if you pick a known convergent series and you do the limit comparison test, then the series that you're comparing to will converge. If you pick a known divergent series and you use the limit comparison test, and you get the limit to be finite and positive, then the series that you're investigating would also diverge. Well, let's see. Oh, I thought a pretty neat statement here is that you use the limit comparison test. Works really good for messy series. Given the series here, there's a lot of stuff going on. You want to compare to just take the biggest term out the series, and that has the most emphasis. So this would be the summation of 1 over n squared. This would be the summation of 1 over the square root of n. This would be the summation of 1 over n to the third. Right? And then we're going to use this theorem to determine whether or not we have convergence or divergence for the given series. So here we compare. If you take the biggest term out of this, this would be n divided by n squared, or 1 over n. So we compare it to the summation as n goes from 1 to infinity of 1 over n. This guy is p-series divergent. So we take the limit as n goes to infinity of n over n squared plus 1 all over 1 over n. So this is the limit as n goes to infinity. This n goes upstairs, so this becomes n squared over n squared plus 1. This limit is equal to 1, where 1 is finite and positive. So that means that whatever happens to this series, the same thing happens to this guy. So this implies or the limit comparison test this series here we compare it to a known divergent series. We take the limit of the ratio, we get a finite and positive number. So whatever happens to the known series happens to the series in question. So what about this one? We compare to the summation as n goes from 1 to infinity of 1 over the square root of n squared. The summation, same thing, as n goes from 1 to infinity of 1 over n, right? We have to start at 1 because at n equals 0, we get something that's undefined. the limit as n goes to infinity of 1 over the square root of n squared plus 1 all over 1 over the square root of n squared, which is 1 over n, but to be comparable to the n squared plus the square root of n squared plus 1. So this is, yes, the limit as n goes to infinity of the square root of n squared all over n squared plus 1. So this is the limit as n goes to infinity of the square root of, we take the biggest term and divide it through, n squared divided by n squared all over n squared over n squared plus, here we're just taking the limit, 1 over n squared. This term here is 1. This is 1. And this goes to 0. So we have the limit of 1 divided by 1. Well, the key is that the limit that you get is finite and positive. And if that be the case, remember, this guy right here is divergent, right? This is harmonic. This guy is divergent. So this implies that the limit comparison test that this series here also diverges. Let's see if we got something that converges. Everything is divergent. I don't like to talk about bad news. Let's talk about some good news. So look at the biggest term. It's that n squared divided by n to the 5. So we compare with the summation as n goes from 1 to infinity of 1 over n to the 3rd, n squared divided by n to the 5th. This is P series convergent. So if that be the case, then we look at the limit as n goes to infinity, 2n squared minus 1 all over 3n to the 5th plus 2n plus 1, and this is divided by the 1 over n to the 3rd. And I need to make this a little bit thicker. Two n. We get the limit as n goes to infinity. This becomes the n to the 3rd times the numerator. So this is 2n to the fifth minus n to the third all over 3n to the fifth plus 2n plus 1. The limit here, since the power of the numerator is the same as the power of our denominator, the limit is the ratio of the leading coefficients, 2 divided by 3. The key here is that this number is positive and finite. So this implies that the given series converges because we're comparing it to a known convergent series. It converges by the limit comparison test. Well, now, what if you're given a problem and they don't tell you to use the limit comparison or direct comparison? You can use whatever test you want, whether it's the nth term test, the p-series, integral, geometric, telescoping, or any of the comparison tests. Let's take this one. I'm going to rewrite this. This is the summation as n goes from 1 to infinity. This is n to the 1/3 divided by n, so we can write this as 1 over n to the, this is 1 minus a third, or n to the 2/3. Right. So let me write it here. N is equal to 2 over 3. The p-series, this guy here is less than 1. And so if p is less than 1, then we said that, or even equal to 1, that is a divergent p-series. So here we use so-called direct comparison. Well, we know here that if you look at this summation, and particularly as n goes from 0 to infinity, that this is a geometric series and it is convergent. So I still use that claim here. So if that be the case, then notice that 5 to the n plus 1 is greater than 5 to the n. And so 1 over 5 to the n is greater than 1 over 5 to the n plus 1. So we have here 1 over 5 to the n plus 1 is less than 1 over 5 to the n. If you know that the series for 1 over 5 to the n is convergent, what do you know about what happens before it? Nothing. So you cannot use the that so-called direct comparison. I still compare it to the summation of 1 over 5 to the n, right? So, which is good. So if that's the case, then here doesn't matter. You can use the so-called limit comparison. So if you think about this limit, since the numerator is less than our denominator even by 1, as n goes to infinity, this guy will go to 0. Well, 0 is indeed finite and positive, but that direct comparison should have worked. This comparison was to a known convergent series, so this also converges. I was for certain, let me put it in blue, I was for certain that I looked at that sometime. So 5 to the n plus 1 is indeed greater than 5 to the n. So 1 over 5 to the n is greater than 1 over 5 to the n plus 1. So 1 over 5 to the n plus 1 is less than 1 over 5 to the n. The series for 1 over 5 to the n converges. What can you say about what happens before that? Nothing. Yep. So now, I have in the past just said by direct comparison this guy converges, and it does. But you use this stupid direct comparison theorem, and it's no help here. The theorem says that if you have one sequence that's less than another sequence, if the smaller sequence converges, then the larger sequence converges. But we're not given that the smaller sequence converges. We're given, well, we pick a sequence out here that's convergent, but it's bigger than these terms. So what happens before that, we don't know. So no problem. We use the limit comparison test. And that may be good for you, that when you're working these problems and you run across something like that, you may get yourself in a hole. You want to back up because somebody would have probably made a false conclusion by thinking that this series right here is divergent. But you're comparing it to a convergent series, but based on the direct comparison, the condition statement is not is not true for this particular problem, for the direct comparison. The limit comparison does work. We get a finite and positive number, 0. We take the limits there. Let's look at this one. So this is good. Look at the limit as n goes to infinity of 2n divided by 3n minus 2 is equal to 2 over 3. It's not equal to 0. So by the nth term test for divergence, the series diverges. And with these series, when they give you an open question like this, where you can use any of these methods, you can use more than one method and you should get the same result. This problem, you can use the integral test, or you can use the limit comparison test. You get the same result. Let's use here the integral test. So here we have the integral of x over x squared plus 1 to be squared dx. Here x goes from 1 to infinity. Let u equal to x squared plus 1. That implies that du is 2x dx. 1/2 du is x dx. So the numerator becomes 1/2 du. So 1/2 times the integral from 1 to infinity of 1 over u squared du. We get 1/2 times the integral from 1 to infinity of u to the negative 2 du. So we integrate, we get 1/2 times u to the negative 2 plus 1 is just negative 1 over negative 1. Evaluate this from 1 to infinity. So we get negative 1/2 times 1 over u, but u is the x squared plus 1. Let's evaluate it from 1 to infinity. So we have negative 1/2 times 1 over, really, infinity, but I'll write it like this, x squared plus 1 as x goes infinity. And then this becomes plus 1/2 times 1 over, plugging x to be 1, we get 2. Now as x goes infinity, 1 over x squared plus 1 goes to 0. And the limit is 1/4. Well, for the integral test, if the integral is convergent, then the series is convergent. We get a number for here, this limit for the integral. So that means that we have convergence. So thus the integral converges, which implies the series also converges. I think that's it.